Chapter 20 is supposed to be a brief diversion from kinetics, and the similarity is that all radioactive reactions follow first order kinetics. So that's probably the single most important thing to get out of this chapter, is that if you see any type of radioactive reaction, you assume the kinetics are first order. And another thing I want to emphasize here is many people hear the word nuclear and they think of bombs and negative and danger. But I wanted to emphasize the important uses that we have of nuclear chemistry today in our lives. That's what's used for radiation treatment for cancer. X-rays are not really nuclear. I'm not sure why they put that here. Nuclear power plants, and toward the end of this chapter, I'll show you the tremendous amount of energy they produce with just a small amount of material. And all sorts of nuclear medicine, and I'll expand on that a little bit too. But there are way more positive outcomes of nuclear chemistry than negative. All right, so a couple of basic definitions. Radioactivity is when a substance spontaneously emits particles or energy from its nucleus, okay? So radioactivity comes from the nucleus of an atom, okay? That's how it's different than regular chemical reactions. Regular chemical reactions involve the electrons around the nucleus. Nuclear changes involve the nuclei. And so we talk about radioactive atoms, and those are the atoms that spontaneously, on their own, decay radioactively. Okay, so I touched upon some of the good applications. Of course, a lot of caution has to be taken, even when we're using it for a good purpose, because as you'll learn in a bit, most radioactive emissions can pass through your skin and body. You probably all know that Marie Curie was able to worked with radioactivity most of her life. That's actually what she died from. She discovered some new elements by observing that they emitted radioactive energy, and for example, radium and polonium. The most important types of radiation emitted are alpha rays. And so now these three most common types of radioactive decay you must know. Okay, so you want to take notes or make a note of these. Alpha rays are emitted from nuclei, and they have a charge of +2 and a mass of 4 atomic mass units. And we usually call those or show them either as for alpha particles, or they are a helium nucleus. They're equal to a helium nucleus. And a helium nucleus has a mass of 4 and 2 protons. So if we're going to use the alpha symbol instead of the helium nucleus, we would do this. And that both of these mean alpha particle. Beta ray or beta particle are simply an electron. Okay. But they are not an electron that originally exists outside the nucleus. They are an electron that comes from the nucleus. And you'll see why a bit later. I know that sounds odd. There are not any electrons inside the nucleus, but it's the decay of a nuclear particle that produces an electron. But for right now, what I want you to know is that the symbol for beta decay is kind of this capital B with a tail. Since they really are equivalent to an electron, they have a mass of about 0. It's negligible mass, and a charge of -1. Okay, so that is the symbol for beta particle. Gamma ray is the third most common type of radioactive emission. And gamma ray is not actually a particle, so it doesn't have mass. It is the highest light energy known to mankind, and it usually accompanies alpha and beta decay. Okay, so it's just high energy, not a particle. We will touch briefly on a couple of other type of radioactive emissions, just so that you're aware of them, but they won't be our focus. There's another type of emission called positron, and another type of radioactive process called electron capture. Here is a summary of all of the nuclear particles that can be emitted with a radioactive species, and here are the symbols that are commonly used for them. The ones I want you to make a note of and know for sure is alpha particle. Here's the sign for alpha. As I said before, you can either use the alpha symbol or you can write He, meaning helium nucleus. Beta particle is typically used with that capital B with a tail. I would prefer you don't use the sign for an electron, because often people get mixed up and think it's originally was an electron. So here's the symbol for beta particle, and really you don't need to worry about positron. You'll learn a bit down the line here that a positron is the antimatter of a beta particle. There really is antimatter. That's not comic book stuff. There is matter that an antimatter that when they meet each other, they annihilate each other. In this slide, we're going to touch on something important that you need to know. Nuclear reactions or processes are written out using the same type of symbols that we use in a regular chemical reaction. But I might, for example, let's look at this one I've written down here. I might, on a test or quiz, write something like this, and I might leave out the product thorium, one of the products, either one of them, and I could ask you, what is produced from the radioactive decay of uranium-238? And then I might say, it decays by alpha decay. What is the other product form? And what's important for you to know is that in any nuclear equation, the sum of the atomic numbers must match on both sides of the arrow. So uranium has an atomic number of 92. We can't lose total number of protons, so as you can see, the atomic numbers both for thorium and helium add up to be 92. The mass numbers that are shown in the upper left of all atomic symbols also must add up or be the same on both sides of the equation. So uranium starts, or this particular isotope of uranium starts with a mass of 238, and the masses of the two products add up to be 238. So if I were to give you this equation in the top and ask you what this product is, you should be able to figure that out with some simple math. All right, I'm going to tell you a bit more of each of the types of radioactive decay. An alpha particle is literally 2 neutrons and 2 protons, okay? That's literally what it is. It's a chunk of the nucleus that gets spit out, and obviously the nucleus it comes from is unstable. And nuclei, as they get larger and larger, as the atomic number goes up, they actually destabilize because, of course, protons, you know, have a positive charge. And when you're cramming all these positively charged particles tightly together in the nucleus of an atom, there's going to be a really, really strong repulsion force. That's part of the purpose of the neutrons, we believe, is they kind of dilute the repulsive forces of the protons. But anyway, as you add more and more protons, your nucleus starts to become somewhat unstable. And when it becomes unstable enough, chunks of the nucleus simply go flying out, and we call that radioactivity. So an alpha particle is a chunk, it's a common one, that contains 2 neutrons and 2 protons. Of course, every neutron and proton has a mass equal to 1 AMU, okay? So remember the symbol for an alpha particle? 1, 2, 3, 4 has a mass of 4, and it has 2 protons. Okay, so that's where that symbol comes from. Okay. The alpha particle is the largest, physically largest particle formed from radioactivity, but it is the least dangerous or least penetrating for people. It's pretty much stopped by a piece of paper. So if you were being attacked by an alpha gun, you just put almost anything in front of you and it would not harm you. So here's an example. Uranium-238 decays by alpha decay to make thorium. This is just a cool picture. It shows an alpha particle being spit out. A beta particle, as I mentioned before, is simply an electron. But it's originally started as a neutron in the nucleus of an atom. But if you have a radioactive element that is unstable, its nucleus is unstable, a neutron that is in the nucleus can decompose and form a proton and an electron. And that electron is called a beta particle. Okay? So what I'm getting ready to say now is very important to know, and it's very easy to get confused about. So pay attention. I would jot notes down. All right, so when an atom decays by beta radiation, so let's look at radon, which does. Here's the beta particle it emits. The atomic number, which of course is the number of protons, increases by 1. So for example, radon has an atomic number of 88. After it emits a beta particle, the atomic number goes up to 89. And of course, different atomic numbers mean different elements. So now we have actinium. And how did that happen? How did we gain a proton by losing an electron? Well, you have to remember where this electron or beta particle comes from. It comes from decay of a neutron, and the side product, in addition to forming the beta particle or electron, an additional proton is formed or made from decay of that neutron. So you have to remember when beta decay, you increase the number of protons by 1. The mass does not change because we make the assumption, since the mass of electrons are so minuscule, we assume that their mass is 0. And this is just a cool picture that shows the summary of beta decay. Another common element that undergoes beta decay is carbon-14 isotope. When it undergoes beta decay, it, of course, becomes nitrogen, gains an atomic number, and the mass stays the same. And finally, gamma emission, remember, it's not a particle. It is a high energy wavelength of light. As a matter of fact, the highest energy that we know of. It is the most dangerous of the 3 common types of radiation simply because it's the most penetrating, can do the most damage to people. It's the kind that gets into your cells and mutates DNA. So gamma radiation, which is, of course, 0 mass, 0 atomic number, because it's a form of energy light, not a particle. Gamma radiation usually accompanies alpha and or beta decay. So when a radioactive nucleus decays, it also releases a huge amount of energy. And so some of that energy is in the form of gamma rays. Okay. So to summarize the penetrating ability of these 3 common radioactive rays, this shows this picture here. So as you can see, beta particles are able to penetrate about a factor of 10 times more than alpha, and gamma rays are able to penetrate about 100 times more than beta. So the way I like to think of it is alpha particle can be stopped by a piece of paper. Beta particle can be stopped by a piece of aluminum foil, and gamma ray requires lead to stop it. Positron, I'm not even sure I'm going to ask you a question, but I have seen questions about it on the ACS final. And so a positron is the opposite of a beta particle. Okay, so let's remind ourselves what a beta particle is. 0 mass and a charge of -1. And the positron has 0 mass and a positive charge instead of a negative charge. If a beta particle and a positron were to encounter each other, they would destroy each other, annihilate each other, and there would just be energy left. So remember we said that a beta particle comes from a neutron that breaks down to form a proton and a beta particle. Positron, instead of the breakdown of a neutron, come from the breakdown of a proton into a neutron and positron. Okay. And so if you're talking about positron emission, instead of the number of protons or the atomic number increasing, the atomic number goes down by 1. Because remember, you're taking a proton and it's decaying into a neutron and a positron. Electron capture is another type of radiation which I'm not likely to ask in my test, but again, I just want to expose you to it in case you see it on the ACS final. But it's basically when the nucleus of an atom pulls in one of the electrons, one of the inner core electrons, one of the electrons that are close to the nucleus, sucks it into the nucleus where it can combine with a proton. Remember, an electron has a negative charge, proton has a positive charge, and when they combine, they can make a neutron. So it's kind of the opposite of beta emission and positron emission, because instead of splitting apart a neutron or proton in the nucleus, you're actually combining a proton and electron to remake another neutron. Okay. And let's see, because a proton in the nucleus has been used up to combine with the electron, the product has one less proton or a lower atomic number than what it started with. This table is a great summary. What you should definitely have committed to memory for my tests are alpha, beta, gamma decay, what their mass is, and what their number of protons or atomic number is. And so, of course, gamma rays have no charge, no protons. Beta particles, no mass, charge of -1. And alpha particle, this is unchanging, but alpha particle has a mass of 4 and a charge of +2 because it has 2 protons. And here's an example of each of them. That is it for the first of 3 pre-recorded lectures from Chapter 20. And the next one is the kinetics of nuclear decay.